We'll get started in just a minute or so, but thank you for being with us. And while we're waiting to get started, we're all very excited here at IWCS. We had our spring meetings a couple weeks ago in Chicago and put together what is appearing to be an absolutely compelling conference in October in Pittsburgh, Pennsylvania, here in the USA. So stay tuned for that information on the preliminary program and the activities that are going to take place. So we hope you'll be able to find a way to join us in Pittsburgh. So more about that later. All right, well, why don't we go ahead and get started? And again, I want to thank you for joining us today. It's good morning, good afternoon, good evening, and I know from the registration we've got some folks late into the evening, so hopefully you have a glass of wine or a beer with joining us from where you are. It's a great audience. So welcome, and my name is Dave Cadieux. I'm honored to be the CEO and director of IWCS, and I will be your host today for this webinar. A few housekeeping items. You are part of a larger audience as an attendee, and with that, all participants will be in listen-only mode. And also, please be reminded that this webinar is being recorded, so you'll be able to see it from the IWCS website or our YouTube channel here in the next several days. And also you can share it with your colleagues. So I'm sure you'll find a lot of really great information from today's presentation. We encourage you to submit written questions at any time during today's presentation using the chat panel. It should be on the right of your screen when you click on chat. After typing in your question at the bottom, make sure to hit the send button, and your questions will be addressed time permitting at the end of the presentation. So look forward to your questions. Today, we welcome Earl Parsons. Earl is a veteran at IWCS, has presented for a number of years, and we really are thankful that he's joining us today to present his paper on chromatic dispersion of single mode fibers for 800 gig and 1.6 terabyte transmission. Earl is the Director of Data Center Architecture Evolution for CommScope. He's located in Texas, USA. He joined CommScope in 2014 as a principal optical engineer. Prior to joining CommScope, Earl received his master's and doctorate degrees in optical science from the University of Arizona, and was a senior member of technical staff at TE Subcom, the old Tyco Electronics. Dr. Parsons also served as an editor of the IEEE 802.3 DB, the 2022 versions, the standard. His interests include multi-mode and single-mode fiber optic systems to enable artificial intelligence data centers, all the rage. So Earl, again, thank you so much for being with us, and take it away.
Great, thank you, Dave, for that introduction. Thank you to everyone for joining the webinar today. So yes, I'm going to talk about single mode fibers, specifically the chromatic dispersion, and how we can better understand that to enable 800G and 1.6T transmission. All right, so this chart is from the Ethernet Alliance showing the roadmap of Ethernet, and the IEEE 802.3 Ethernet creates standards for new data rates. So over time, we have adopted and published standards for faster and faster link speeds. 800G was the latest published last year with the .3DF standard, and that has applications where there are 8 100G lanes, and now the 802.3 DJ project is working on standards for 800G and 1.6T using 200G lanes. And then of course they've got added this year is the 3.2T port speed that will be coming sooner than later, rather than later. Each time we develop a standard for a new speed, there's new challenges to overcome. It's harder and harder to squeeze more bandwidth out of the transceivers, out of these links. So in this talk today, I'm going to focus on the wavelength division multiplexing, or WDM, applications that use 200G signaling. So here's a chart illustrating the 802.3 DJ objectives, which is the big project in Ethernet standards right now. We have different media, from copper cables to single mode fiber, and different Ethernet rates and different signaling rates. So I'm focusing on the 200G signaling rates, primarily looking at 800G FR4, that's a duplex 2 kilometer application, and 800G LR4, also duplex fiber 10 kilometers. Both of these have 4 wavelengths that are multiplexed onto one fiber for transmit and another fiber for receive. So we want to look at the impact that single mode fiber chromatic dispersion has on these WDM applications, even though the things that we learn can also be applied to the parallel single mode fiber applications like the 800G DR4 and the 800G DR4-2. So understanding single mode fiber chromatic dispersion is key to developing standards for 800G and 1.6T, particularly for those 200 gigabit per second signaling, and particularly for the ones that have wavelength division multiplexing, where you have multiple wavelengths on a single fiber. So as we go to higher and higher speeds, chromatic dispersion becomes a major limitation for data center applications. Every time we double the baud rate, and for .3 DJ, we're looking to double from 50 gigabaud to 100 gigabaud, or 100 gigabit to 200 gigabit, because we're using PAM4 signaling, we quadruple the penalty from chromatic dispersion. So that happens for 2 reasons. One, as we go to higher baud rates, to double the baud rate, we half the symbol period. So we're getting a unit of data at double the rate, so we have half the time between symbols of data. And at the same time, as we have a higher baud rate, we widen the spectrum of the signal, we increase its bandwidth, and we increase the difference between the longest and the shortest wavelength in that signal, in that wavelength channel. So those 2 things combined lead to a quadrupling of the chromatic dispersion penalty. So chromatic dispersion is specified in I2T standards, and for data center applications, we're going to focus on G.652 and G.657 standards, fiber standards. The 652 is your traditional fiber, and the 657 is the bend insensitive fiber. And these standards include 2 parameters that define the chromatic dispersion of a single mode fiber. The first is the zero dispersion wavelength. So here I plot dispersion in picoseconds per nanometer and kilometer versus wavelength for a couple example fibers. And the zero dispersion wavelength, which is where it crosses the 0, is specified to be between 1300 and 1324 nanometers. And the second parameter is the slope of the line at zero dispersion. So that can be in a range 0.07 to 0.092 roughly. So here I have 2 example fibers with the extremes of that's allowed by the standards. This has the shortest zero dispersion wavelength, this one has the longest, and they have this one has a more extreme slope and this has a more shallow slope. And if we look at the different wavelengths we're using in data center applications, from 1264 to 1337 nanometers, we can see these 2 fibers will have very different amounts of dispersion. This blue fiber would have nearly double the amount of negative dispersion at the shortest wavelengths, and the orange fiber would have nearly double the positive dispersion at the longest wavelengths. So each transceiver is going to see a different amount of fiber dispersion depending on what fiber is actually being used in the path. And it's important to understand this relationship and what's the variability, what are the options, what are we actually seeing for chromatic dispersion. So previous Ethernet standards before the .3 DJ project would specify and test each transceiver to be able to tolerate the maximum possible dispersion from the most extreme fibers allowed by the standard. So each transceiver would be specified and tested to handle nearly -6 picoseconds per nanometer kilometer at 1264 and like 2.5 or more for 1337, even though not all fibers are going to have those extreme amounts of dispersion at those wavelengths. So we set out to take a more statistical approach to understanding fiber chromatic dispersion and to see how often do we see these extreme fibers, what are the more common fibers and amounts of dispersion that would be seen in the fields. So to do that, I created a data set of different fibers, looking at their zero dispersion wavelength and their slope, and created that data set using fibers that have been found in CommScope cables over the last few years. So this data set ended up having more than 2.5 million fiber spools, and each spool was a 50 kilometer or so fiber spool from a fiber manufacturer. These fibers were manufactured from 2013 to 2024, looked at fibers that had the traditional 250 micron coating diameter, as well as the newer 200 micron coating diameter that we're seeing. All these fibers were compliant to the relevant data center fiber standards, the G.652.D and or G.657.A1 and A2, which are the bended sensitive ones. These fibers came from manufacturers all over the world. There were 6 fiber manufacturers represented, and they had factories in North America and Europe and in Asia, including in China. And if we look at the market share of the 6 fiber manufacturers in this data set, they represented 64% of the market share. So felt confident this is a good or representative sample of fibers that have been deployed in the field for data center markets in the recent past. In parallel, at the same time, the I2T did a study where 8 fiber manufacturers participated, and they submitted their statistics for dispersion. And if we look at those 8 fiber manufacturers, they represent about 68% of the fiber market. So here we have some results from the data set from the CommScope fiber. Here I plot dispersion in picoseconds per nanometer and kilometer versus wavelength. The black dashes are the I2T max and min. So that's the most extreme fiber that would be compliant to those standards, the amount of dispersion we would have. And we want to particularly pay attention to the positive dispersion at 1337 nanometers and the negative dispersion at 1264 nanometers. The blue dots and the orange dots are the max and min dispersion from the most extreme fiber in the data set. And we can see that, if we compare this black dash to this blue dot and this black dash to this orange dot, the most extreme fibers in this data set of 2.5 million fibers weren't as extreme as what was allowed by the standards. So that gives us an idea that things aren't as bad as we sometimes assume. Here I have a bivariate histogram where I look at the zero dispersion slope and the zero dispersion wavelength versus the number of occurrences in this data set. And this base of this figure is the entire range allowed by the I2T standards. So zero dispersion wavelength from 1300 to 1324 and a slope up to 0.093. And we can see the vast majority of the fibers are in this very narrow range with a moderate wavelength and a moderate slope. We do have some fibers that are at the extreme of zero dispersion wavelength, but they have a slope that's lower than the max allowed by the standard. And we do have some fibers with a very high slope, but their zero dispersion wavelength is kind of in the middle. So all of these are moderating effects. The worst case, the most extreme fibers that would create the most dispersion for transceivers would be the ones that would be located in this corner and this corner back here, where we have the maximum slope and an extreme zero dispersion wavelength. And we really don't see many of those fibers. Here I have some histograms that show that the vast majority of the fibers in this data set had much less dispersion, positive and negative, than what would be allowed by the I2T standard. So here I have, again, dispersion in picoseconds per nanometer and kilometer for 1264 nanometers, 1337. These are the two 800G FR4 extreme wavelengths. And then on the bottom, I have the two wavelengths for 800G LR4. Again, that's the 10 kilometers for 1294 and 1310 nanometers. The vertical red lines here are, again, the most extreme that would be allowed by an I2T standard. And we see that, again, nearly all the fibers are well away from that chromatic dispersion limit. Especially want to pay attention to this limit right here. This is the most negative we'd see, and over here we'd have the most positive. And yeah, there's a lot of daylight between where we see those fibers and that standard. So again, this indicates that if we design and specify and test each transceiver to tolerate these extreme dispersion amounts, maybe we're over-engineering our transceivers. And as we get to faster and faster data rates, where each doubling of the baud rate quadruples the chromatic dispersion penalty, that's a cost that the market is not going to sustain. We need to be a little more careful about how we specify things and how we understand the link channel for these transceivers when writing our standard, so that we can make transceivers and data rates that are economically feasible and technically feasible at the same time. And I think this statistical approach helps with that quite a bit. All right, so one concern when we were discussing this in IEEE is we wanted to make sure that the data set we're using to understand the statistics of these single mode fibers and their chromatic dispersion parameters, that they're a representative sample. So one concern was, if we look at fibers that are being manufactured today, does that apply to fibers that were manufactured in the past? When fibers are installed, especially in campus or outdoor environments, the installers want them to last for a long time, for decades. So here I look at the per kilometer dispersion for a number of different years of the fibers in this data set. So I plot histograms from 2014 through 2024, fibers manufactured in those years. And I focus on the FR4 wavelengths, 1264 and 1337. Again, those are the more extreme. They're both and longer than what we see in the LR4 applications. And we can see there's not a lot of variation. We see some difference in the histograms from year to year, but they're all pretty close. So this gives us good confidence that if we look at the statistics of fibers that were manufactured recently, well, that's going to give us a good indication, good understanding of what was manufactured in the over the last decade or so. Here I have a chart of the 99% values. So it'd be the 99% on this tail for 1264 and this tail for the 1337, and I have the two wavelengths there. And I have this blue on the left is the 99% value for the entire data set of 2.5 million fibers. And then I have the 99% value for each subsequent year. And then the final one, this periwinkle color, is if I take all 10 years and combine them with equal weight, what's the 99% of that histogram? And we see a little bit of variation, maybe on the order of tenths of picoseconds per nanometer and kilometer, but this is remarkably stable. So very good news for this data set, that it is a good representation of what's been deployed in the field for quite a long time. Another concern was where we have different types of fibers and different manufacturers. So the first type of fiber we looked at was looking at the coating diameter. So traditionally, single mode fibers have a 250 micron coating diameter, but more recent fibers have a 200 micron coating diameter. The idea is if we can decrease the size of the coating diameter, we can get higher density in the cables. That's very important for a lot of these hyperscale data centers where cables can have thousands of fibers in one cable. So here I have the 99% values again for 1264 and 1337. The blue is the entire data set. The orange is the 250 micron fibers, and the gray is the 200 micron. We see the 200 micron has a slightly less dispersion than the 250, but it's also a very small part of the data set. Again, these fibers are newer. They haven't been as widely adopted as the 250 micron. Then the other case is to look at the different fiber manufacturers. We have that on the bottom. Again, for 1264 and 1337. The blue is the entire data set. The red is if we take all 6 manufacturers and weight them equally and look at the 99% value of that histogram, we see it nearly matches the entire data set. And then the orange bars and the gray bars are for the 2 extremes from the different 6 fiber manufacturers. So if I look at each of the 6 individually, look at their tails, the 99% value, they all range between the orange and the gray bar. So there's some variation, but again, not very much. So it's a good indication that this data set can be used for the statistical analysis. And it's not surprising because fiber manufacture has been around for decades. This is a mature, established industry. A lot of really smart people have done a lot of work to improve the processes and make a very stable and viable product. So we understand the data set. It's a good data set to do the statistical approach. The next question is, how are we going to use this data set to come up with actual numbers that we'd put in a standard to understand the channel of the fiber and that single mode chromatic dispersion? So we have a few different options, and these were hotly debated in IEEE, and I think we ended up with good understanding of what the pros and cons of each approach was. So in the next few slides, I'll have a couple of different approaches, and I'll define them here. So if we think of the different fiber manufacturers, we could think of their dispersions having histograms like we saw on the previous slides, but each manufacturer would be slightly different. They might have different means and standard deviations between them. So one approach to using this data set to determine the dispersion we would use in the standard would be what I call the most extreme single distribution. So with this, I'd look at the leftmost tail of the leftmost distribution, the blue one here, and the rightmost tail of the rightmost distribution, which would be this yellow one, and use that. This is a more conservative approach. This would ensure that no matter which of the fiber manufacturers are being used, then we aren't underestimating the dispersion we could see. Another approach is we could make a mixture distribution, combine these different distributions into a larger distribution, and then look at the left and right tail of that entire data set. So we did that in 2 ways. One is just to look at the 2.5 million fibers as they were ordered from my employer. The other is to do a mixture distribution with equal weight, where we combine these 6 different manufacturers equally, and then look at the left and right tails of that distribution. All right, so here I have the dispersion statistics for the 800G FR4 wavelengths for a single segment of fiber for 2 kilometers. So again, the FR4 wavelengths are 1264 and 1337. I have a single segment, or M equals 1, as the nomenclature we developed. The reason is, or what that means is, we consider the entire 2 kilometer link is consisting of a single fiber, one continuous fiber. There's no different cables, there's no splicings, one continuous fiber with one dispersion value. So we chose one segment because thinking that the campus network is the limiting case for FR4. We can imagine a data center campus where you have multiple buildings and they could be connected by a 2 kilometer cable and FR4 optics on either end. This would be one where you have maybe very short patch cords inside the building, but the vast majority of the link length is dominated by that campus cable that's running between the 2 buildings. That would be nearly 2 kilometers long. So here I plot the CDF versus dispersion. For 1E minus 2, that'd be a 99% confidence interval, 99.9, 99.99, and 99.999% confidence for these different values here. The vertical red line, again, is the max and the min allowed by the I2T. This would be what the dispersion you'd have for the most extreme fiber, the most extreme wavelength, the maximum slope that would be allowed by the I2T standards. So the blue dots are the most extreme single distribution. Again, that's looking at the left tail, the leftmost distribution, the right tail, the rightmost distribution. And we can see there is a difference. There is less dispersion, both negative and positive, using the most extreme single distribution compared to the maximum, the most extreme allowed by the I2T standard. The red would be the mixture distribution, and then the green is the mixture distribution where the 6 manufacturers are weighted equally. Now, finally, we have the yellow dots. These are from that I2T study I mentioned before, where 8 different fiber manufacturers participated and shared statistical data about their fiber distributions. And the I2T approach took that same most extreme single distribution. So the yellow and the blue is the same or similar methodology. And we see a little bit less of a benefit, but still a benefit. There's still an improvement that could be made to the understanding of the channel that makes things easier for the transceiver manufacturers if we look at any of these dots compared to the traditional approach of assuming the most extreme case. All right, we have this similar approach for the 800G LR4 wavelengths. Again, this is a 10-kilometer application where the wavelengths range from 1294 to 1310 nanometers. And in this case, we took m equals 4. There's 4 segments in this link. So out of the whole 10 kilometers, it consists of 4 2.5-kilometer segments. The reason we went with 4 segments of 2.5 kilometers each is as you look at these really high fiber count cables that could have thousands of fibers in a single cable, you can't make a cable that's longer than 2 or 3 kilometers. If the cable is much longer than that, the spool is too big to put on a truck, so about 2.5 kilometers is what's practical to ship with modern fibers. So this helps with the statistics because as just the way statistics work, if you take 4 samples and continue to consider them in aggregate, you do have a benefit compared to assuming a worst case. So again, we have the confidence levels. The vertical lines are the maximum allowed by I2T. The blue dots are the most extreme single distribution from my data set. Again, left tail, leftmost manufacturer, the right tail, the rightmost manufacturer. The blue dots are from the I2T study, similar methodology, different data set, but we get remarkably good agreement between the yellow dots and the blue dots. So that was really exciting to see. And then the green is where we have a mixture distribution where we weight the 6 manufacturers equally. So we see a larger benefit in this case than we did for the 2-kilometer FR4 applications. And again, this difference between these dots and these vertical lines means less dispersion that the transceivers have to tolerate, because we understand the channel a little bit better, and we realize that these most extreme fibers are incredibly rare, and we don't have to always design to accommodate them. All right, the results of the I2T study were released and published last year. If you look at the 2024 update of G.652 standard that is available on I2T's website for free in Appendix I.6, they list their methodology, list the values that I include in the yellow dots in those previous slides. So a treasure trove of information from the I2T. And this was, some of those numbers were adopted or have been adopted in the 802.3 DJ standard that's under development. So the results are in the G.652 standard, but they also apply to the G.657 fibers. So those are the more popular bend-insensitive ones that are around now. And the data includes the statistics for a range of wavelengths, not just the 4 wavelengths I've highlighted here. and also for different number of segments. So I looked at 1 segment for the FR4, 4 segments for the LR4 applications, but the I2T study goes up to, I think, 16 different segments. So very useful information for the industry. All right, so that helps us understand what to do for 200G lanes, again, for 800G FR4, 800G LR4, but this industry is not slowing down. People want faster and faster data rates. We now need to understand what to do for 400G lanes. So this work shows that a statistical approach to chromatic dispersion can lead to less stringent requirements for 800G and 1.6T transceivers. So we don't need a new fiber standard for these applications, and we don't need to push the transceivers as hard as they need to for the fields. The data set in the study used fibers that are in CommScope cables, and were compared the results to the I2T study that had 8 different fiber manufacturers participating. So like I said, 400G is coming. So there are efforts in IEEE right now to look at what are the requirements, including the requirements of single mode fiber for 400G lanes. So these 400G lanes could enable a 1.6T transceiver that would have 4 lanes of 400G, or 3.2T lanes or transceivers that would have 8 lanes of 400G. So we could talk about 1.6T FR4, 1.6T LR4, very high data rates to meet the demands that are being put on the industry. So if you're interested in that, if you look at the IEEE Ethernet standards website, the new Ethernet applications for AI is the best place to find those resources that have been presented to what are the requirements that we need for 400G lanes. And one question ongoing is, would we need a new single mode fiber standard to support this high data rate? This study that I present today shows we don't need a new fiber standard for 200G. Do we need one for 400G? If we needed one, I would propose considering it with these shapes here. So here I have zero dispersion slope and zero dispersion wavelength. The dotted rectangle here is all the values that are allowed, all the combinations of those 2 parameters allowed by I2T standards like G.652, G.657. And like I said earlier, the ones at the top right and left corners are the fibers with the most extreme dispersion. They're going to have the biggest penalty on transmission. So if we needed a new fiber standard, we could just lop off these 2 top corners, have more of a trapezoidal shape. That would help. That would be the easiest way to get a benefit for the transceiver manufacturers without causing a real undue burden on the fiber manufacturers. It's still an open question if we'll even need that. So we'll stay tuned. Maybe we'll have an update in the future about chromatic dispersion for 400G lanes. All right, thanks everyone for attending, and thank you IWCS for this invitation. If you have any questions, I'm happy to answer them now. I also have my email there. Feel free to reach out to me.
Earl, thank you again so much. This is kind of where the rubber hits the road in moving photons and the accuracy of what's sent and what's received. And I guess that opens up a question and also an observation. The question is, you mentioned the practicalities of 2,000 to 2,500 or 2 kilometer to 2.5 kilometer lengths because of just practical transportation of the products. But do you see, as we gain the capability for this data transmissions, up to 3.2 terabytes and things like that, the technology required for transceivers and repeaters, through the campus, and then obviously the ultimate objective is across communities and countries. How do you see that technology component coming along?
Yeah, so every time we go to a higher data rate, we've got to innovate. We got to improve the technology and make those changes. So I think one thing that's interesting, because you mentioned, kind of these longer reaches, if you're going across a community or like a metro network or your ultra long haul, it's a different transceiver technology. Everything I've talked about today is intensity modulation and direct detection, where we're changing the power of the signal and looking at the relative power to determine what are the bits that are being transmitted. There's another transceiver technology called coherent transmission, where you change the phase of the signal instead of just the intensity. And that's been around in like the ultra long haul and the undersea networks for about a decade. And each generation that becomes more cost effective and lower power, so it's more attractive to shorter and shorter reaches. So we're seeing that propagate from the really long reaches down to the shorter. We might see that in the 10-kilometer spaces in the future. And one interesting thing about those coherent transceivers is they are a lot more tolerant to chromatic dispersion than our traditional intensity modulation direct detect transceivers.
Right. Well, and obviously the opportunity here is for the technologies of artificial intelligence and quantum computing. And I will mention Earl resides in Richardson, Texas, with CommScope, and a lot of activity at the University of Texas in Dallas, looking at the quantum computing physics and opportunity. But also there's a potential for a test bed being generated in the Richardson, Texas area. A lot of work with government and universities, but companies like CommScope as well in Richardson, to really employ this technology, because where the opportunity is how's the infrastructure, transmit what is going to be required for extreme amounts of data, through photons, and how do we use this technology like Earl has just described, both in terms of the link and the fiber, as well as obviously the equipment that needs to go along with it. So with that, Earl, what is the impact of this technology? How will it impact artificial intelligence and data centers, and then transmission across communities and campuses?
Yeah, that's a great question. So AI is a hot topic everywhere, and fiber communications it's no exception. It's really driving a lot of what we're doing in all kinds of efforts, whether we're looking at fiber or transceivers. So right now, the AI data centers are the ones pushing for the faster and faster data rates. They'll be the first adopters of these 800G, 1.6T, 3.2T transceivers. So there's a need for lots of data for these AI data centers, and they need to move that data around quickly. And so what I've talked about today is more of the campus level, maybe
Right.
across the, maybe some data centers are big enough you need 2 kilometers in the building, but a lot of it's on the campus. Your AI clusters typically have either your parallel single mode fiber or your multi-mode fiber. So it wouldn't impact so much like at the cluster connecting the GPUs, but you have different GPUs or AI factories, as some people call them, in different buildings on a campus. You're going to need this high-speed connectivity.
Yeah. So a specific question about the technology: does the statistical approach to dispersion increase the chances of any link failures in the field?
That is a good question. Yeah. So if we look at some of these confidence levels that I was illustrating, we might say, well, a 99% confidence interval is not very high. We traditionally want something higher than that. So again, these top dots would be 99%. We want something higher for these fiber networks. We want to make sure things work and are up. But for things not to work, a lot of stars have to align, right? If we consider in order for this, for say we propose something, a dispersion for a transceiver around these values, even though this is the worst possible. Even if the link has more dispersion than what we'd expect with our confidence level, a lot of things have to go wrong for the link to actually fail. We have to have a transceiver that's operating at that extreme wavelength, right? We looked at, say, 1294 and 1310, but that's the most extreme of that wavelength channel. There's a range that they can operate in, and most manufacturers tend to go to the middle or the less extreme wavelengths. So we'd have to have a transceiver with extreme wavelength. We'd have to have all 4 fibers segments to have an extreme dispersion parameters. We'd have to have a transceiver with no margin. A lot of things have to go wrong at once for to have a link failure. So I think the statistical approach, we can still have confidence that these links are going to work.
Very good. I see no further questions, but I do, again, a couple shameless plugs here. As we've put together our IWCS program for October, the conference in Pittsburgh, this technology, this capability for AI and machine learning and quantum computing in the future, we are going to have a couple different special sessions that are going to incorporate both the theory and the opportunities as well as the practicality. And these kinds of solutions and future standards are going to be discussed. So I hope that you'll plan to participate in those discussions and special sessions at the conference. And again, the opportunity in Richardson, Texas, with a lot of really impressive work going on down there, the potential for a quantum computing corridor in the United States. And there's several of these going on throughout the world. I know in the UK there's also collaborations between government and university capabilities and doing test analysis. But if you wish to participate, any of your companies in these programs and these test opportunities for these future technologies, just let us know and we can hook you up with the right folks. But we're thankful that CommScope is already actually situated down there, and we trust that your company will also be a participant. So with that, we'll go ahead and wrap up today's webinar. I am providing you. Hold on one second. Just I lost here. There we go. So I'm providing you with Earl's contact information, his email address, if you want to reach out to Earl directly with any follow-up questions or comments. Again, his paper was presented at the IWCS 2024 event, if you want to seek that out. And we do conduct these technical webinars every month, sometimes a few more per month based on opportunities with specific companies. But typically our technical paper webinars are on the 3rd Friday of every month. And our next webinar is on June 20th at 10:30 a.m. Eastern USA time. And it'll be a very interesting topic on sustainability and fluoropolymer approaches in support of cable and connectivity. So please, you'll receive information on that webinar, and feel free to share these announcements with your colleagues so that they can join as well. It's important that we recognize our partner level sponsors for IWCS, who greatly provide not only financial resources but content as well. And without their strong leadership and generosity, we'd not be able to bring these important technical innovations and information to you and our global community. And again, we thank CommScope not only for today's webinar, but for their endless support of IWCS. And again, as I mentioned earlier, we held our IWCS spring meetings of our board and community. Our conference. What am I trying to think of? Oh, anyway, we have a very wide group of individuals who help support our conference and create the program based on the abstracts that we have received. And so we now are in the process of putting that preliminary program together, inclusive of the special sessions. So please stay tuned to receive that information, and mark on your calendars the October 27th to 30th date in Pittsburgh, Pennsylvania, USA. And we hope that you'll be able to join us and come learn a lot more about where this technology is going. So again, we want to thank Earl for today's event and all of you for joining us. And we hope you have a great weekend, and look forward to seeing you again next month. All the best.